Hey, Mark. How's it going over there?
We're doing good.
Good stuff. No more clean room. I'm 6 hours ahead of you guys, so I'm home for the day.
Lucky.
Wow.
How's it going?
Good. Somebody asked him a question.
Sorry, dude, are you looking at the ceiling?
Kind of.
Yeah, a little bit. That's better.
Putting in half of breakfast.
Yeah.
Alright, take it away, man.
All right. Yeah, what's up, guys? So my name's Kevin. I am right now. I'm in a PhD program for particle physics, and I go to a university in New York called Stony Brook University. And at the moment, I am living in Europe, working at CERN, actually, doing some of my PhD research. So I wanted to mainly just have a conversation with you guys if you had any questions or anything. But to sort of set the stage and give you a little bit of context, I actually made some slides. So I'll go ahead and share my screen and say a few words about that. And then we can have a little Q&A or discussion. You see my screen? Sorry, those are some engineer drawings.
What are these spy documents we see on here?
Alright, so like I said, I'm in particle physics. Specifically, I'm an experimentalist, opposed to a theorist who works with equations. I actually like to build things and design experiments. So I want to tell you a little bit about what being an experimental particle physicist means. And so in this picture right here, actually, this is a machine that we have here at CERN. This is one of the several detectors that the LHC, the Large Hadron Collider, has. They collide protons or other elements into each other and look at what happens. So for scale, there's not me, but there's a guy right here. So you can see this is a really massive machine. So experimental particle physics. The idea behind particle physics is to study energy and matter at the smallest scales, the most fundamental way possible. So we study the fundamental building blocks of nature and the interaction between those particles. So in this picture below is sort of a schematic of the standard model of particle physics. And there are, you can see just a few matter particles. There's a dozen right there, but in your everyday life and all the material that's around you in the classroom right now, only 3 of them exist: the up quark, the down quark, and the electron. And I think that it's really cool how these 3 particles interact with only 4 forces, and it's very simple kind of and at the most fundamental level, but all of this really rich chemistry and a variety of materials and all these different phenomena can occur from just these few particles and a few simple rules of how they interact with one another. So in Parker's class, you'll learn about all the chemistry and the different ways that these particles come together to make some really cool phenomena happen. So as an experimentalist, like I said, we build things and design experiments to make careful measurements of these particles and try to understand how nature how it works, really, the structure of nature. And I really enjoy doing this kind of work because I get to help build some really magnificent machines and come up with different technologies to try to answer what I think are some really deep and profound questions. And just as an example, there are a few of them down here. One of them that my research is actually centered around is, how is it that the universe came to exist the way that it does today? It sounds kind of vague, but actually it's a sound scientific question. Why do we happen to exist the way that we do? Why is there the matter that there is in this world, and why does it interact the way that it does? You can imagine an infinite different number of possibilities of how things could happen. Why do we find ourselves to be in the position we are now? Other questions like, how did the universe begin? What is the origin of the universe? And ultimately, what will the fate be of the universe? You know, as we evolve, what's gonna happen? Will it end? If so, how will it end? So these are the sort of questions that are behind all of the sort of research in particle physics. They're usually not told in such a kind of grandiose way. There are more specific questions behind it that research try to tackle, but at the end of the day, we try to weave them all together and understand these sort of questions. So that's sort of what particle physics is in general. I wanted to give you a little flavor of this in action with an experiment that I'm actually working on, which is called DUNE. It stands for the Deep Underground Neutrino Experiment. So neutrinos are some of those fundamental particles that you saw on the last slide, and they're one of the most recent discoveries among those fundamental particles, and we don't understand them as well as some of the other ones. So it's an exciting bit of research to be involved with, and it's kind of shifting the particle physics community, shifting its focus from high energy to this sort of research. So this is a multi-billion-dollar experiment that relies on contributions from thousands of scientists from literally all over the world. So it's really cool. It's one of the things I like about my work, actually. I get to travel around everywhere. Like, for example, right now I'm living in France and I commute into Switzerland to work. Later in my PhD, I'll be going to Japan and working on an experiment there. And then, of course, I'm based in the US. So it's really neat to be able to meet people from all over the world and travel. So the experiment has three main parts. One is an intense source of these particles called neutrinos. So those are made in Illinois, and we have the second component, which is a detector right near the source, which kind of characterizes what kind of particles we're producing in the beginning. And then we shoot those particles through the Earth's crust 800 miles to another suite of detectors in South Dakota. And these detectors, the ones that I'm involved with building and designing, the idea right now is to put 4 modules that will build up this far detector complex. And each one of those 4 modules is about the size of your school gym. And they contain 20 million pounds of argon. You're breathing in argon right now, actually. It's 1% of the atmosphere. So every time you inhale, 1% of that breath is argon. But we're going to cool that argon down to minus 300 degrees Fahrenheit, and it will actually liquefy. And the majority of our detector is this liquid argon. And then we put some electronics in there to see the trace of neutrinos that go through that argon. But we're going to build this huge detector almost a mile underground. So we're going to excavate this huge cavern to hold these detectors, and we're going to move all of the components individually, one by one, down this shaft that's a mile long. And this detector, when we build it a mile underground, it's sensitive enough to detect neutrinos, and that's actually not a trivial statement. To build something that can detect neutrinos is not easy to do. For example, we're not very good neutrino detectors. Right now, there are trillions of neutrinos passing through your body every second, and we don't even notice it. So that fact right there is why we need, one, a really intense source of neutrinos from Illinois, and also we need a huge detector in South Dakota underground to have any chance of detecting even just a handful of these particles. So I'll just leave it at that and kind of open it up for some questions if you guys have any questions about that or anything else.
If neutrinos are able to pass through us, what really are they, like, basically?
Yeah, so that's a good question. They're, I mean, just like an electron, which I think you've started to talk about in this class, the electron that goes around the atomic nucleus, it's a fundamental particle just like that. The reason that they pass right through us is, so I mentioned there are 4 fundamental forces, right? One of them is the electromagnetic force, and that's the one that keeps the electron bound to the nucleus. However, the neutrino doesn't feel that force. And every time there's contact, you touch a table or any sort of contact when you play football and people tackle each other, those forces are essentially electromagnetic. That's kind of the driving force. That and gravity are the driving forces that we experience kind of in our day-to-day life. But neutrinos don't feel the electromagnetic force. So that's why they don't interact very much. The force that they do feel is called the weak force, and it's appropriately named because it doesn't make things interact very strongly. It's weak. It's a good question.
Thank you.
Anything else?
So, what do you like most about your general work with particle physics?
Well, yeah, no, there's a lot of things I like about this. I already mentioned that I love that I get to travel a lot. I get to meet a lot of really cool people from all around the world, and I like the different types of work that's involved. So there's a lot of hardware where I'm. New ways of doing things. I hadn't thought of before. Sorry, are we lagging a little bit? I think the connection's kind of poor.
Yeah.
Did you catch any of that?
Unfortunately not, no.
No. Okay. Let me go inside when the connection's a little better. Alright, let me start over. Okay. Yeah, so I mentioned that I like the fact that I get to travel around the world and meet a bunch of really cool people. I also like the creative aspect of this, right? So it's not just you're given a problem, you kind of have the blueprints of how to solve it and you follow those steps. You have to really be creative and come up with new ideas to be successful in this field. I think that's fun. I also like the fact that there's a lot of different types of work that you do. So you get to do hardware work, which is kind of the project I'm working on right now. Is I go in the lab and I build things. So you get to work with your hands, which I like. There's also a lot of software and programming, which is really valuable and fun, to be honest. And the biggest part that I like about this is the end goal. Like, why are we doing all this? To answer some really interesting questions. And I think that's something that's really kind of tied to, what makes us human. I think we wonder about things. And I think that this is kind of the pinnacle of wondering and going out there and trying to find answers. So I like the end goal, and I like the things that you do to get there.
Thank you.
Of course. Thanks for the question.
Hey, so, alright, so you said you're working with the CERN Super Collider?
Yeah.
Okay, so like in The Simpsons they have...
Not on the collider, but that's, yeah.
Okay. So like in The Simpsons they have like the black hole like on and off switch. I know that's like obviously a joke, but is it like an actual possibility for that to happen?
I mean, so it's really not. No, in some sense, I guess it was. I mean, we know it's not now because the machine's already been running at this energy. The reason people were, I guess, worried about that was that you're creating conditions that have very high energy density. So a lot of energy in a very small amount of area, or small amount of space, volume, I should say. And those are the sort of conditions that can make a black hole, but nowhere near the sort of energy densities that we're making at CERN. It needs to be much more than that. You need to have some really, really violent events in the universe to make that happen. For example, you need a star to explode, and it needs to be a really big star. It can't just be any stellar explosion. It has to be a really extra violent one. So, no, there's no chance of creating any black holes.
Okay, thank you.
Rest assured, we won't get eaten up in a black hole tomorrow.
Also, how long does it take to make a machine like that, like that big?
That's good. So, for example, the detector that I showed you, the Dune FAR detector, we've been planning that for something like a little over a decade already, and we haven't even started to build it yet. Okay, so there's a lot of R&D, research and development that goes into it. The technology that we're building has never been built at this scale. It's a really huge detector. So there's a lot of kind of scaling up that is involved with that. So at Fermilab, which is the national lab in the States, they've done a lot of kind of smaller scale prototypes of the detector. And at CERN, we're building 2 bigger prototypes still. So that takes the prototype that I'm building is about 1/20th of the size of one of the modules of the FAR detector, and this is taking us 2 years to build. So it's a really, I mean, there's going to be more people involved for the big one, so it won't scale exactly like that, but it's going to take several years to build it once we start. But right now, we're just tweaking the design and make sure we understand the technology and everything before we invest $2 billion into building it. The one that I'm making, the small one, is $50 million. So it's still not a small project, but much less than the $2 billion machine.
Hopefully that works out for you guys.
Thanks.
How do you get the funding for something like that? Like, where does the funding come from, and how do you get that much money for projects?
That's a really good question. So the main source of funding for this experiment is the Department of Energy, DOE. So you guys are paying for it, all the taxpayers. Some of that money goes towards science like this, which is a good thing. I mean, a tiny bit. Most of the tax money goes to things like the military, but some of it gets funneled towards science. But this particular experiment, Dune, is so big that it actually is an international collaboration. So there are not only the U.S. government is putting money up for it, but governments from all over the world are contributing money and manpower to make this thing happen. Good question. There's also other funding agencies in the U.S., like the National Science Foundation, a lot of other. There's one guy at my university who was a mathematician and a physicist, and then decided to go into the financial world and made a lot of money by analyzing the stock market. And now he's ridiculously rich, and he puts his money into science. So he funds a lot of people's projects and everything. So there are a lot of different ways, but most of it comes from government funding.
Do you ever get really stressed, like, knowing that you're working with, like, a really big funded project that's multi-million? Like, does that ever, like, is there ever a time where you're just, like, really stressed out about that kind of stuff?
Not really, actually. Not really, because, I mean, like I said, there are 1,000 people plus working on this, so the stress is kind of distributed among all of them, right? I know that if I go to work today and I don't get anything done, or if I break everything, it's not going to ruin the project, right? In the long run, you know, I'm just one piece of the puzzle, and there are a lot of other pieces. But there's a little bit of stress involved. But, you know, we all kind of share that stress, so it doesn't crush one person.
All right, thank you.
Of course.
Stop it. What made you get into this field?
What got me in physics? So when I was in high school, I really liked math. I liked kind of the logic of it. You know, there's a right answer and there's a way to do it. And I liked my science classes. I liked my physics class, but really the whole year I wasn't that interested. I appreciated the method and again how kind of logical it was, but I wasn't that interested in it because we were just doing things like swinging pendula and trying to find relationships between how far you let it go from and how long it takes to come back. That didn't really interest me. But at the end of the year, my professor or my teacher in high school gave a talk to the class about some of the more modern efforts in modern physics. And he showed me pictures of these machines, some of which I just showed you guys, and he told me some of the questions that are really deep questions that they're trying to answer. And then it really hit me, wow, you can be logical and come to kind of reasonable answers to questions that are this big and this profound. Then I really kind of thought about science differently and decided to study in college and ultimately pursue a career in it.
You just talked about answering questions. Is there a question that you really want to answer through science?
I'm sorry, I couldn't hear you very well.
In your presentation, you talked about answering the question how the universe was created. Is there a certain question that you want to answer?
Yes, actually, it's a good question. So what I would like to answer with this Dune experiment. Okay, so the picture I showed you had all of the different matter particles, right? There's about a dozen of them. That's actually only half of the picture because there's also the same set of particles called antiparticles. So for the electron, you have an anti-electron, which is the positron. And for all of those particles, they have a sort of sister particle, and it's called an antiparticle. So if these two particles, if you have an electron and an anti-electron come in contact, they annihilate one another and turn into pure energy. There's no more matter there. And the idea is at the Big Bang, it produced out of nothing pairs of particle and antiparticle. But after time, all of these pairs should have hit each other and annihilated. So there shouldn't be any matter here right now. So that's a big outstanding question in science. Why is there any matter in this universe? Why are we here? Like, those are the sort of questions, right? Why are we here? I wouldn't think that, when I was in high school playing with pendulum and everything, I didn't think that I could answer questions like, why are we here scientifically? So that's one thing that I would like to answer. Why do we find ourselves in a universe that's dominated by matter and essentially void of antimatter?
Thank you.
Thank you for the question. These are all great questions.
So earlier you were talking about how the universe was beginning and how it might end. What do you think, or how do you think the universe is going to end if it does?
I really don't know. I couldn't tell you. I can tell you there are a couple different theories, right? There's one called, so I said the Big Bang is kind of what we call the beginning of the universe. You have nothing, there's this big explosion that spews energy and matter into the cosmos. There's two, as far as I can remember, two theories of how it might end. And that is a big crunch, where all of that matter that got shot out kind of eventually starts to collapse on itself and comes back to that same point. And then there's another one where all of that energy and matter gets shot out and it just keeps shooting out. And eventually space is expanding, so eventually it becomes so cold and that matter and energy becomes so diffuse within that space, and there's so much space in between particles that it essentially just freezes out. So that's called the big freeze. And those are two ideas of how the universe may end. It'll be a long time from now, though. So there's also other things about that have to do with kind of instability of particles, but it's too technical. But people have ideas of how it may end, but we don't know when or how.
I love you. You guys have anything else?
Start the revolution.
Ask him.
I can show you.
Okay.
He showed me
Mr. Singleton, do you have any questions for him?
Yeah.
Yeah.
Full science is Friday.
Oh,
Are you
like
unprepared? Are you unprepared? Single
Personal questions?
Single
Ask him a question.
How you doing?
Alright, if you guys don't have anything else for Kevin, then I'll let him go. Angela has a question?
I don't know.
Yes, she does. Yes, she does.
I don't have a question.
Doesn't have a question.
How you
I got a
doing?
question.
Thank you, Mr. Kevin.
Okay, everybody thank Kevin.
Thank you,
Pleasure. See you guys.
Before you leave.